Have you ever looked at the world around you and thought it all made perfect sense? You drop a ball and it falls. You push a door and it opens. For centuries, this was the world of classical physics. It was a comfortable, predictable place, governed by clear rules. Newton's laws told us exactly how planets would orbit and apples would fall. Everything had a cause, and every cause had a predictable effect. It was a beautiful clockwork universe. You could, in theory, know the position and speed of every single particle and predict the entire future of the cosmos. But then, about a century ago, scientists started peering into the world of the very, very small. They looked at atoms, electrons, and photons, and what they found down there was not a neat clockwork at all. It was a bizarre, bewildering, and utterly strange reality. The quantum world is famously weird. Particles can be in multiple places at once, a bit like a ghost haunting several rooms simultaneously. They can pop in and out of existence from nothing. They can even be connected over vast distances, instantly affecting each other in a way that Albert Einstein called spooky action at a distance. To understand the big debate in quantum physics, we need to talk about a very big idea: determinism. Imagine you are playing a game of pool. You hit the white cue ball at a specific angle with a specific amount of force. A physicist could, with enough information, predict exactly where every single ball on the table will end up. Every bounce, every collision, every final position is determined by the initial hit. This is a deterministic system. It's like a line of dominoes. Once the first one is pushed, the fate of all the others is sealed. There is no randomness, no surprise. For a long time we thought the entire universe worked this way. This idea is called determinism. It suggests that if you knew the exact state of everything in the universe at one moment in time, you could calculate the entire past and future. But quantum mechanics threw a massive spanner in the works of this clockwork universe. It introduced the idea of indeterminism. For example, when will a specific radioactive atom decay? Quantum mechanics says there is no way to know for sure. It's like the universe is constantly rolling a set of cosmic dice to decide what happens next. Imagine you are lost in a thick fog. You can't see more than a few feet in front of you. Your path seems random and unpredictable. But what if there was a map? What if there was a hidden guide whispering directions that you couldn't hear, leading you along a very specific, predetermined path? This is the core idea behind pilot wave theory. It was first proposed in the 1920s by a brilliant French physicist named Louis de Broglie. He had a radical idea. What if quantum particles, like electrons, are real solid particles with a definite position at all times? And what if, in addition to this particle, there is also a wave? A real physical wave that acts as a guide or a pilot for the particle. The particle never loses its identity. The weirdness of the quantum world comes not from the particle itself, but from this mysterious pilot wave that it surfs upon. The wave flows and ripples through the universe, and the particle is pushed along by it, like a piece of driftwood carried by the currents of the ocean. Let's dive a little deeper into this idea of a predictable universe. Imagine you are standing on a cliff overlooking the sea. You are holding a small, smooth stone in your hand. If you drop it, you know exactly what will happen. It will fall. Gravity will pull it downwards at a very specific rate. You could even predict the size of the splash it will make. This is the world of classical, deterministic physics. A French scientist named Pierre-Simon Laplace took this idea to its ultimate conclusion. He imagined a vast intellect, now often called Laplace's demon. This demon would know the precise location and momentum of every single atom in the universe at one specific moment. With this knowledge, the demon could calculate the entire future and past of the cosmos. It's like watching a movie that has already been filmed. Every scene, every line of dialogue, every plot twist is already on the reel. The future is already written, and the past is unchangeable. This deterministic dream dominated science for a very long time. It gave us the power to build bridges, send rockets to the moon, and predict the weather. Now let's zoom in, way in, forget about planets and stones, and think about something much smaller, like a single electron. This is where the comfortable, predictable world of classical physics breaks down completely. When scientists started to probe this tiny subatomic realm, they found that the rules were different. The clockwork was gone. replaced by something that looked more like a casino. Imagine a single atom of a radioactive element like uranium. This atom is unstable. At some point it will decay, spitting out a particle and transforming into a different element. When will this happen? Classical physics would say that if we knew everything about the atom, we could predict the exact moment of its decay. But quantum mechanics says something completely different. It says there is absolutely no way to know. The decay is a truly random event. It's like the atom has an internal clock that ticks randomly. So we have this big fight between two ideas. One says the universe is a predictable clock, the other says it's a game of chance. But what do we really mean when we say something is random? Let's think about a simple coin toss. We call this a random event. But is it really? If you had super-sensitive instruments, you could measure the exact force from your thumb, the spin rate, the air currents in the room, the coin's precise center of mass, and its starting orientation. With all that information, a powerful enough computer could calculate exactly how it would land. The coin toss only seems random because we are ignorant of all these tiny details. This is the kind of randomness that determinists like Einstein could accept. Is the randomness we see in quantum mechanics like a coin toss, where there are hidden details we just don't know? Or is it something truly, fundamentally and irreducibly random? The story of this forgotten path begins not with a seasoned professor in a dusty lab, but with a young French prince. His name was Louis de Broglie, a nobleman who initially studied history but found his true passion in the abstract world of theoretical physics. In his 1924 PhD thesis, he put forward an idea so bold and so strange that the examination committee was unsure if it was genius or nonsense. They even sent it to Albert Einstein for his opinion. At the time, physicists were wrestling with a puzzle known as wave-particle duality. Sometimes things like electrons and photons acted like tiny solid particles, like little billiard balls. At other times, they behaved like spread-out waves, like ripples on a pond. How could something be both a particle and a wave at the same time? De Broglie proposed something different. He said, why can't they be both simultaneously? He suggested that every particle is a real solid particle, always accompanied by a wave. This wave is also a real physical thing. De Broglie called it a pilot wave. Let's try to build a clearer picture of this particle and its guide. Imagine you are on a small surfboard in the middle of a vast, dark ocean. You are the particle. You are a solid object, located at one specific point on the water's surface. The ocean itself is the pilot wave. It has ripples, currents, and huge swells that stretch out far beyond your sight. You, on your little board, are completely at the mercy of the water. Where the wave is steep, you move quickly. Where it is flat, you slow down. The complex motion of the ocean dictates your path. In pilot wave theory, the electron is the surfboard. It always has a well-defined position. The quantum wave function is reimagined as a real physical wave field, the ocean. The particle doesn't just float randomly on this wave. Its velocity is directly and precisely determined by the shape of the wave at the particle's exact location. The wave can sense the presence of a measuring device or the layout of an entire experimental setup. It then transmits this information back to the particle by changing its shape, thus altering the particle's path. So how does this pilot wave actually guide the particle? The connection is incredibly intimate and precise. The particle surfs the wave, but not in a simple way like a board on water. The particle's velocity at any given moment is mathematically determined by the gradient or the steepness of the pilot wave at the particle's exact position. If the wave is changing rapidly in a certain direction, the particle is pushed strongly in that direction. If the wave is smooth and flat, the particle moves slowly or not at all. This idea explains one of the central mysteries of quantum mechanics, how a particle can have wave-like properties. Consider the classic example of diffraction, where a wave bends as it passes through a narrow opening. In pilot wave theory, it's not the particle itself that bends, it's the pilot wave. As the wave passes through the opening, it creates a complex interference pattern on the other side. The double-slit experiment is often called the most beautiful and mysterious experiment in all of physics. It perfectly captures the core puzzle of quantum reality. When you fire particles like electrons one by one at a barrier with two slits, they behave in a very strange way. If you only have one slit open, The electrons land in a simple clump behind that slit. But when you open the second slit, the electrons create an interference pattern. Pilot wave theory offers a beautifully straightforward explanation. The electron is a real particle with a definite position. It does not go through both slits. It can only go through one slit. However, its pilot wave is a real extended wave. Just like a water wave, the pilot wave goes through both slits simultaneously. On the other side, the two parts of the wave meet and interfere with each other. The electron particle, having passed through its chosen slit, now encounters this complex interfering pilot wave. The wave essentially pushes the particle away from the dark stripes and directs it towards the bright stripes. To really grasp the difference between these two views, let's imagine two chefs trying to bake a cake. The first chef represents the Copenhagen interpretation. This chef is a bit of a magician. They start with a bowl full of potential cake ingredients. The ingredients don't really exist as separate things yet. The moment they decide to observe the contents, something magical happens. Poof! The cloud of possibilities instantly collapses into a definite set of ingredients. Now let's look at the second chef, who represents pilot wave theory. This chef is a meticulous planner. They believe reality is not magic, just very complex. They know from the start that the bowl contains real flour, real sugar, and real eggs. The ingredients have always been there, with definite properties. The problem is the ingredients are invisible to the chef. But the chef has a secret tool, a recipe wave. This wave flows through the kitchen, and its shape is determined by everything in the room. The recipe wave is the hidden information. One of the biggest headaches in quantum mechanics is something called the measurement problem. It's the question of what counts as a measurement. In the Copenhagen view, a particle exists as a wave of many possibilities until it is measured. But what is a measurement? Does it have to be a human scientist? Does a camera count? What about a cat looking at it? The Copenhagen interpretation divides the universe into two separate realms with different rules without clearly defining the border. Pilot wave theory elegantly solves this problem by simply erasing the line. In this view, there is no fundamental division between quantum and classical worlds. Everything from a tiny electron to a giant star, to the physicist making the measurement, is made of particles guided by pilot waves. Now let's tackle that famous spooky action at a distance, or quantum entanglement. Imagine you have two entangled coins. They are linked in such a way that if one lands heads, the other will instantly land tails, no matter how far apart they are. The moment you look at your coin and see its heads, you instantly know the other one is tails. The Copenhagen view says that neither coin had a definite state until you looked. Pilot wave theory offers a completely different explanation. The two entangled particles are like two surfboards riding on the same single ocean. This pilot wave connects them and stretches across the entire distance between them. The particles are not truly separate. They are two parts of one interconnected system. It's like two puppets in different rooms being controlled by the same puppeteer, whose hands are connected to both. So, if pilot wave theory offers such neat solutions to quantum puzzles, why isn't it taught in every university? Part of the answer lies in simple history and timing. When de Broglie first proposed his idea in the 1920s, the Copenhagen interpretation, championed by charismatic figures like Niels Bohr and Werner Heisenberg, quickly gained momentum. It became the winning team. By the time David Bohm revived the theory in the 1950s, the Copenhagen interpretation was already deeply entrenched. Overthrowing it would require extraordinary evidence. A mathematician named John von Neumann had published a proof that seemed to show that no hidden variables theory could reproduce quantum mechanics results. This proof was later shown to be based on a faulty assumption, but the damage was done. One of the biggest conceptual hurdles for many physicists when it comes to pilot wave theory is its explicit non-locality. The pilot wave connects distant parts of the universe. This seems to fly in the face of Einstein's theory of relativity. Relativity tells us that nothing, not even information, can travel faster than the speed of light. How can the pilot wave instantly change its shape across the galaxy? Defenders argue that this non-local influence cannot be used to send a practical signal. You can't use your entangled particle to send a faster-than-light message because you can't control the random outcome. The mathematics of pilot wave theory is also often considered more cumbersome and less elegant than the standard quantum formalism. While it might be more intuitive conceptually, working out calculations can be much harder. Another major argument against pilot wave theory is that it feels somewhat contrived. Critics argue that it was specifically designed to reproduce quantum mechanics results, but in a deterministic way. It adds an extra layer of reality without offering new, testable predictions. Science generally prefers theories that are simpler, a principle known as Occam's razor. This perceived lack of new predictions has kept the theory on the sidelines. Why invest time and resources into a more complicated version of a theory we already have? However, this situation may be changing. In recent years, some physicists have begun to suggest that there might be situations where it does make different predictions, often involving quantum cosmology or quantum gravity. If a theory like pilot wave is correct, it means the universe is deterministic. Everything that happens is the unavoidable result of what came before. But what about us? We are also made of particles. The atoms in our brains, the electrons firing across our synapses, would also be following these predetermined paths. This leads to a profound question. If every atom in my brain is following a script written since the Big Bang, what does that mean for my free will? Do I really choose my actions, or am I just a complex puppet? Think about the choice you made to read this article. It felt like your own decision, but in a fully deterministic universe, this choice was inevitable. This challenges our most basic sense of self. If our choices are predetermined, does that mean we are not responsible for our actions? All our moral and legal systems are built on the assumption that we are free agents. However, some philosophers argue that even if our actions are predetermined, the experience of choosing is still real and meaningful. The sheer complexity of the human brain makes it practically impossible to predict its behavior. Let's step back from our own minds and look at the wider cosmos. What would a deterministic universe, as described by pilot wave theory, actually feel like? The surprising answer is, it would look and feel exactly like the one we already live in. The determinism is hidden. Imagine a perfectly balanced roulette wheel. To us, the outcome seems utterly random. But in reality, the ball's final position was determined from the very start by its initial speed and position. A deterministic quantum world is like that. The cosmic dice are loaded, the game is fixed. But because we can never know the hidden details, the outcomes will always look random to us. This has a profound implication. It suggests that the universe is not fundamentally weird or paradoxical. It is orderly, logical, and governed by strict laws of cause and effect. If we were to discover that pilot wave theory is the correct description of reality, it would trigger a revolution in physics. The primary goal of fundamental science would shift. Instead of being content with calculating probabilities, physicists would be emboldened to search for the hidden layer of reality. The focus would turn to understanding the nature of the pilot wave itself. The search for a theory of everything would be seen in a new light. The explicit non-locality of the pilot wave might be a clue about the true nature of space-time at the quantum level. A deterministic framework could have practical implications. By learning how to manipulate pilot waves, we might gain finer control over quantum systems, leading to breakthroughs in quantum computing, material science, or nanotechnology. We have journeyed through the strange and wonderful landscape of the quantum world. We started with the familiar clockwork universe of classical physics, then plunged into the bizarre realm of the quantum. The standard Copenhagen interpretation tells us to accept the weirdness as fundamental truth. But we also explored a forgotten path, pilot wave theory, which paints a radically different picture of reality. So, we are left with two profound and wildly different stories. One gives us a universe of inherent chance and observer-created reality. The other gives us a universe of hidden information and absolute determinism. Choosing between them has been more a matter of philosophical taste than scientific necessity. Do you prefer a reality that is fundamentally mysterious and probabilistic, or one that is orderly and deterministic, but with a crucial part hidden from view? For many decades, the debate was stuck in a philosophical stalemate. Because both theories made the same predictions for all experiments, there was no way to prove one right and the other wrong. It was like having two different instruction manuals for a car that both perfectly described how it runs, but gave completely different explanations for how the engine works. The path forward is to escape pure philosophy and make a new, testable prediction. Researchers are currently looking at the most extreme corners of the cosmos, exploring areas where our current theories break down, such as inside a black hole or during the first moments of the Big Bang. Even without a unique prediction, pilot wave theory continues to serve a vital purpose. It acts as a powerful critical tool, constantly challenging the assumptions of the standard model. So what are we to make of all this? Could reality truly be deterministic? Could every event, from the flicker of a distant star to the thought you are having right now, be part of a grand, unbroken chain of cause and effect set in motion at the dawn of time? The idea is both magnificent and unsettling. It presents a universe of profound and beautiful order, a single coherent story unfolding according to unbreakable laws. It suggests that the chaos and randomness we perceive are just shadows on the wall of our cave, hinting at a deeper, more elegant reality that lies just beyond our grasp. This is a universe that Einstein would have loved, one where God does not play dice, but instead presides over a majestic and perfectly choreographed cosmic dance. It is a return to the classical dream of a fully intelligible world. Ultimately, we do not yet know which story is true. The quantum world continues to guard its deepest secrets. The Copenhagen interpretation remains the textbook view, but pilot wave theory stands as a compelling and beautiful alternative. It shows us that a deterministic reality, free of paradoxes, is a logical possibility. The quest to understand the nature of reality is one of the oldest and noblest of human endeavors. Pilot wave theory reminds us that what we see is not always all there is. It encourages us to keep questioning, to keep exploring, and to keep searching for the hidden order that may lie beneath the surface of our strange and wonderful universe. Whether the universe is a cosmic coin toss or a perfect clockwork, the journey to find out is what truly defines us as thinking beings in this vast, mysterious cosmos. The search continues.